All right, in this video, we are going to be talking about factors that influence resistance of vasculature, specifically. And we're going to use Poiseuille's equation, which is an equation for tubes, okay? Vasculature, essentially tubes, that's what it is. Now, the equation goes like this. It's 8 times the viscosity of the liquid times the length of the tube divided by pi times the radius of the tube to the 4th power. Okay? That is, it seems like a lot, but let's talk about it. Okay, viscosity, what is that? That's essentially the thickness of the liquid. Kind of makes sense, right? If you have a thicker liquid, then it's going to encounter more resistance. It's going to be more slow moving, like molasses, right? As opposed to water. Molasses is more viscous than water. It's going to encounter more resistance in the tube. Okay, the length of the tube. The longer the tube is, the more resistance the liquid's going to encounter. It's like the difference between trying to suck out of a short straw and a really long straw, those crazy straws. It's a little bit harder to suck out of those crazy straws because the longer tube creates more resistance, okay? And now this is what's really interesting. An increase in radius, just doubling the radius, does a lot more than just change the resistance by 2, okay? What doubling the radius does is it's actually going to decrease the resistance by 16 times. This is pretty incredible. So a small change in the radius or the diameter of a blood vessel can result in great changes in resistance. And let's think about how we know that changes in radius actually influence resistance. If you have a much wider tube, then it makes sense that things are going to be able to get through that more easily than a really tight pinched off tube, right? It's going to be harder for things to get through that. Okay, so bigger radius means less resistance. Longer tube means more resistance. More viscosity also means more resistance. One thing I wanted to talk about specifically with blood. So viscosity in this case is going to be related to our hematocrit, the amount of red blood cells present. Higher hematocrit, more viscous, lower hematocrit, less viscous, okay? Last of all, we can add resistances to each other, and this is where I wanted to use this diagram a little bit more. There are 2 ways to add resistance together. It's in series and in parallel, and I just want you to understand what series and parallel means. So series is this artery plus this arterial plus this capillary plus this venule plus this vein plus this bigger vein, the ones that line up right next to each other. We add those resistances together just like adding integers, right? A plus B plus C plus D and so on and so forth. You just add them together. But you can also add resistances in parallel, okay? An example of parallel are all of these capillaries, right? They're not attached to each other. They don't line up with each other. They are parallel to each other. And the way we add them like that is 1 over the resistance of this capillary plus 1 over the resistance of this capillary plus 1 over the resistance of this capillary, and so on and so forth, is equal to 1 over the total resistance of all of those blood vessels that are in parallel, okay? And that's all I have on resistance. I will continue the series in another video. Thank you for watching.